When you know enough about numbers and sets, and you're familiar with modern notation of math, we can start talking about basic operations of linear algebra. You all should be familiar with two-dimensional or three-dimensional vectors from physics and calculus courses. Vectors are defined by size and direction, and you can draw it from the origin to some point in space. For example, in two-dimensional case, with coordinates of x and y, you can draw some vector to the point AB, where A is x coordinate of that vector, and B is y coordinate of that vector. Similarly, in three dimensions, you have x, y, and z. And then you start at origin, and you have some specific vector, which gets here. So this is A, B, C coordinate, which means that here you have A, here you have B, and this one is C. If we want to generalize vectors to more dimensions, it is obviously makes sense to expand the list of 2 or 3 numbers with more numbers. So if we had list of A, B, then we had list for 3 dimensions of A, B, and C, we will want to define general vector like that, as a set of numbers of that kind, where you have n numbers. Each of those numbers or elements of that set should belong to real numbers or complex numbers. So technically, this sign means belongs to R multiplied by R multiplied multiple times by R and n times. The m by n matrix is defined by the following table of numbers. The matrix dimensions are m and n. Pay attention that the first dimension is always number of rows, so this is number m, and the second dimension is always number of columns, so this is number n. That kind of matrix has dimensions m by n. Note that the first index of all of the elements of the matrix, which is that element, and that element, and all of those elements are basically number of row. The second element is always number of column. So column 1, column 2, until we get to column, which is the last one, column n. So that matrix, let's call it A, we can also write a set of numbers I, J. I will always represent row, and J will represent column. Note that vectors could be written as a row or as column vector. In linear algebra, we discern between those two types of vectors. They are not the same, even if all of the elements are the same. For example, the vector 1, 2, 3 is not the same as vector 1, 2, 3. To convert all columns to rows and vice versa, we use transpose operator. This is superscript T. For example, 1, 2, 3 transpose equals 1, 2, 3 vector. Or, if you're talking about matrices, you also can do the same thing. 1, 2, 3, 4, 5, 6 matrix transpose equals to 1, 2, 3, 4, 5, 6 matrix. Basically, I took the main diagonal and flipped that matrix that way by the main diagonal. And this is how I got to that matrix. So basically every element changing their direction, and so on. Similarly, if you have vector 1, 2, 3, transpose, you can get back to the vector 1, 2, and 3. If you take more complicated matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're doing transpose to that matrix, this is what you get. So every element Aij is technically replaced with Aj. This is how you make transpose. So all of the main diagonal stays as is. Now the number 2 will exchange with this number. Number 3 will exchange with this number. Those numbers also will exchange. And what we get is basically 1, 4, 7, 2, 5, 8, and then the last row is 3, 6, and 9. This is how you make transpose of the matrix. Note that vectors are a particular case of matrices of 1 by n or n by 1. Sometimes we are putting dimensions near the matrices or near the vectors. For example, this vector here, this vector is 3 by 1, and this vector is 1 by 3, because you have 1 row and 3 columns. This matrix is 2 by 3, 2 rows and 3 columns. This matrix is 3 by 3. Now I want to define a few simple operations on vectors and matrices, addition and subtraction. To add or subtract vectors or matrices, they have to be of the same size or dimension. When they are, the addition and subtraction is made element-wise, 1 by 1. For example, if you're taking vector 1, 2, 3 and adding vector 3, 4, 5, the result will be just 1 plus 3, two plus 4, and 3 plus 5. So you're doing that element-wise. First element with first element, second element with second element, and so on. And the result, of course, will be 4, 6, 8. Another example. You have matrix 1, 2, 3, 4, 5, 6. You want to add, or let's try to subtract, another matrix of the same side, same dimension. So number of rows and number of columns should be the same. Let's say 6, 5, 4, 3, 2, and 1. So we're doing that element by element. 1 minus 6 first will be minus 5. 2 minus 5 will be minus 3, and so on. Here you get minus 1, 1, 3, and 5. This is the result. Pay attention that dimensions should be exactly the same. So if you're starting with matrices which are 3 by 2, and this one should be also 3 by 2, the result also should be 3 by 2. Another simple operation on vectors or matrices is a multiplication by a scalar. Scalar is just some real number that you're multiplying by. You can think about scalar also as matrix with dimensions 1 by 1. So it's just a number. So how you multiply by scalar vector or matrix? You're taking that number, let's say 5, multiplied by a vector 1, 2, 3, and you multiply it element-wise. So you're multiplying 5 by each element in the vector or in the matrix. So in that case it will be 5, 10, and 15. Similarly for matrices, 1, 2, 3, 4, you can multiply by 5, and then you'll get 5, 10, 15, and 20, and you'll get back matrix of the same dimension. Pay attention that this operation is very useful in linear combinations and matrix multiplications that we will see in a moment. Linear combination is one of the most important building blocks in linear algebra, which we will use to define multiplication of matrices, but it also has multiple engineering applications in optimization, controls, neural networks, and others. Given a list of vectors like v1, v2, v3, and so on to vk, and let's use some underline to show that this is vector and not scalar. The linear combination is defined by the following thing. It's alpha 1 multiplied by v1 plus alpha 2 v2 and so on, alpha k multiplied by vk, where alpha belongs to real numbers or it belongs to complex numbers. Note that you can think about alpha coefficients, alpha 1, alpha 2, and so on, as the relative weights of the vectors v1, v2, and so on. So each vector has its own weight, and when you multiply a scalar by vector, you get vector of the same size, of the same dimension, which means that the entire expression here is also vector of the same dimension as all of the vectors v1, v2, v3, and so on. Let's take a simple example of combination of 3 vectors, which are 1, 2, 2, 3, and 3, 4. So this is our v1, v2, and v3. Linear combination of those vectors will be alpha 1, 1, 2, plus alpha 2, 2, 3, plus alpha 3, 3, 4. Now we can put everything together. So it will be alpha 1 multiplied by 1 plus alpha 2 multiplied by 2 plus alpha 3 multiplied by 3. And the second element will be twice alpha 1 plus 3 times alpha 2 plus 4 times alpha 3. So you get vector. The original vector was 2 by 1, and the result is also 2 by 1, because this is just real number, and the second one is also real number. So you have vector of 2 real numbers. Now we can use linear combination to define multiplication of matrix by a vector. Let's say we have some matrix A, which is defined as a table of m by n real numbers. So the dimension of matrix is m by n. Note that everything I will be giving you in that lecture will work also for complex matrices, but I will continue only with real numbers in the matrix just to make things a little bit simpler in terms of explanation. So this matrix could be multiplied only by column vector and not by row vector. So column vector should be of the size n by 1. This is the only size which will work for multiplication of matrix by a vector. So pay attention that this n is the same n like here. So this is very important property, that you cannot multiply just any matrix by any vector. Only matrix of m by n could be multiplied by a vector which is n by 1. So this vector x from n dimensions, which means it has n elements. The result will be column vector with m elements. So the overall result of that multiplication will be another vector with b1 to bm. This multiplication is defined the following way. You taking and dividing that matrix, which we can call A, into columns. So you're taking first column, second column, and so on until you get to the last column. Each column gets its own weight, and those weights are given in the second vector. Weight x1, x2 until you get to the weight xn. You're taking x1 and multiplying by the first column, which is here, plus second one multiplying by the second column, and so on until you get to the last element of the vector multiplied by the last column of the matrix. As you may see, that entire thing is linear combination of matrix columns with the weights which are given in the vectors that you are multiplying by. Now, note something very interesting here. So what will be the result of that kind of computation? We get a11 x1 plus a12 x2 plus and so on plus a1n xn and so on until you get to a m1 x1 plus a m2 x2 plus and so on a mn multiplied by xn. This is the vector b. Okay, generally you can write that as ax equals b. So multiplication of matrix A by vector x equals vector b. But pay attention to something very interesting. If you're looking on that line, essentially what you're doing, you're taking first row in the matrix and multiplying element-wise by that column vector. Okay, and then you're adding all of the results. So you're taking a11 multiplied by x1 plus a12 multiplied by x2 and so on, and adding them all together. To get the last line, which is here, you again taking the last row of the matrix and multiplying by vector x, element by element, and adding all of the elements together to get the last element. So technically you can look on the multiplication of matrix by vector from different perspective. You can think about that as multiplication of each row by column vector, and this will be the result b that you are looking for in the multiplication. Now I want to define another very useful product of two vectors, multiplication of two vectors. This is called inner or dot product of two vectors a and b. Those two vectors should be of the same length, of the same size, and this size should be n. So if we assume that vector a equals a1, a2, and so on to an, and vector b is b1, b2, and so on, bn, their dot product will be the sum of their element-wise multiplications, which means something like that. So you're taking first element in vector a, multiplying by first element of vector b, plus second element of a by second element of b, plus, and so on, last element of a by last element of b. This is how you write that formally as a formula. This is just sum of ak, bk, where k runs from 1 to n. And clearly the result of that computation is a scalar. So it's just a number. It's not matrix and not vector, because you're adding only elements of the vector, and all of those are just numbers. And when you add in scalar numbers, you still get scalar. Let's take a simple example. You want dot product of 1, 2, 3, is big dot 4, 5, 6, the result will be 1 multiplied by 4 plus 2 multiplied by 5 plus 3 multiplied by 6. And the result will be 32. Note also that it doesn't matter if I'm using column vectors or row vectors, the dot product will always be the same scalar, and in that computation it doesn't matter at all. There are a few important properties of dot product or inner product. First of all, you can write dot product as multiplication of two vectors. So for example, if both vectors are column vectors and A looks like that and B looks like that, so this is vector A and this is vector B, then A transpose B will be equal that vector multiplied by that vector. Note that this is exactly A1, B1 plus and so on plus AN, BN, which is exactly dot product between A and B. This is the first property here. Now, A dot B is the same as B dot A, so you can switch the order of dot product, which is pretty obvious. If you multiply some vector or one of the vectors by constant alpha, it could be any real or complex constant, you can take that alpha out of the parentheses here. And then it will be alpha multiplied by dot product of alpha of A and B. Or you can multiply first B by the same constant, and then A will be outside of that dot product. All three of them are equivalent. And then you have distributive law, which says that dot product of vector A with sum of two vectors B and C is basically dot product with the first one plus the dot product with the second one. This is a very important property and we are using that a lot. I want to give you some caution note here, and I want you to understand that since this is multiplication, it has some similarity to regular multiplication of the numbers, but this is not the same thing. You get as a result scalar number here, but still not all properties of multiplications of numbers are correct for dot products. For example, if A dot product with B equals A dot product with C, you cannot cancel A easily here. Because if it would be simple multiplication, it would be basically B equals to C. But this is not true in that case. What is true is that A dot product with B minus C equals to 0. And this is because of that last distributive law. But this does not mean that in that case A equals to 0 or B minus C equals 0. Or in other words, B equals C. Here is a simple example. Let's say A equals 1, 1, B equals 0, 1, and C equals 1, 0. So clearly A is not 0 and B is not equal to C. But let's see what we get from here. So A dot product with B is basically 1 multiplied by 0 plus 1 multiplied by 1, which is 1. A dot product with C will give us 1 multiplied by 1 plus 1 multiplied by 0, which is again 1. So they both equal. You can check also that thing. So 1 dot with B minus C, so it's 0 minus 1 multiplied by minus 1 plus 1 multiplied, and B minus C for the second element is 1 minus 0, so it's 1. So totally it gives us minus 1 plus 1, which is 0. So that thing works, but clearly A is not 0 and B is not equal to C. Okay, now let's try to understand geometric meaning of dot product, what it means to do dot product between two vectors. I will demonstrate that in two-dimensional space because there it's much easier to see the meaning of it. Let's say we have two vectors. And those are two vectors we are talking about. And let's say we have some angle theta between those two vectors. I will call the first vector A and the second vector B. Now, since we are talking about origin here, this distance will be the size of A, and this distance will be the size of B. Now, the question is, what is Z vector? I want to remind you that this vector is basically vector B minus A. This is a vector. Generally, sometimes it's difficult to remember maybe which direction I need to put that arrow. But if you think about very simple trick, you can understand why I put that arrow that direction and not the other way around. Because first of all, if this is vector B minus A, then this is vector A plus the vector B minus A, which is A plus B minus A, should give you vector B. And this is what it does exactly. Now, that distance between vector A and B, we will denote as B minus A distance. Now, if I want for that triangle that I've got between those two vectors, and you can think about that as vectors in some coordinate system, but it's not important in that case. So if I write cosine theorem for that triangle, this is what I will get. So from cosine theorem we know that this side, which is B minus A squared, equals the first side squared plus the second side squared minus twice first side, second side, and cosine of the angle between them. And you have multiplication here. Now let's try to simplify that a little bit. We know that the coordinates of vector A, which is A1, A2, and coordinates of vector B are B1, B2, and this means that technically A equals square root of A1 squared plus A2 squared, and similarly here from Pythagoras theorem this is square of B1 squared plus B2 squared. Now similarly for the third side, from Pythagoras theorem, by B minus A squared will be B1 minus A1 squared plus B2 minus A2 squared. This is clearly true because this is Euclidean distance between the point A and point B. So this vector is basically between the point A and point B here. Now let's put all of those numbers inside of the definitions that we've got before. So you have B1 minus A1 squared plus B2 minus A2 squared equals A squared, which is A1 squared plus A2 squared plus B1 squared plus B2 squared minus twice square root A1 squared plus A2 squared, B1 squared plus B2 squared, and cosine theta. Let's simplify a little bit. Now let's make a few cancellations. b1 squared, b1 squared, a1 squared, a1 squared, b2 squared with b2 squared, and then a2 squared with a2 squared. What left is basically minus twice a1 b1 plus a2 b2 equals minus twice a b cosine theta. So you can cancel also 2 and minus. And then what we've got is the following. So pay attention to that term. This is actually a dot product with b vectors. So a dot b equals size of a multiplied by size of b multiplied by cosine of angle between them. This is essentially what dot product means. It's just multiplication of the sizes of the sides of the vector, of the lenses, by cosine between them. Now pay attention to very important property. If dot product equals 0 and the vectors themselves are not zeros, it means that theta equals 90 degrees, which means that the vectors are orthogonal. This is very important property, and sometimes you want to find orthogonal vectors. This is how you detect orthogonal vectors. This is one of the most important properties of dot product. Now we are ready to learn how to multiply two matrices. Two matrices, A of the dimension m1 by n1 and B with the dimensions m2 and n2 could be multiplied only if their internal dimensions are the same. So n1 equals to m2. This is a condition. Otherwise you cannot multiply those two matrices. This is very important. Now the result will have dimensions which is m1 by n2. This is the dimension of the result. So for example, if you have matrices 5 by 2, you can multiply it by another matrix which is 2 by 7, and the result will be 5 by 7. Before you multiply matrices, you need to make sure that you know the dimension of the result. Otherwise you will have many troubles computing those matrices. Now formally, the multiplication is defined by the following formula. Technically this formula says something like that. If this is my result, so this is element ij in the output matrix, which is multiplication matrix, something that I get from the multiplying matrices A by B. So if I want that specific element in the matrix and its location is ij, and I remind you that I is a number of row and j is a number of column, I'm just taking the matrix A and taking row number I in the matrix A and column number j in the matrix B and making dot product between those two. This dot product will give you, of course, real number, which will be here as a result. So you're taking i's row and j's column, multiplying them as dot product, adding, basically multiplying element by element, adding all of the elements, and this is what you will have at that point ij in the result. Here is one theoretical example of how it works. For example, your matrix A is 4 by 2 and your matrix B is 2 by 4. So the result will be 4 by 4, and you can multiply it because 2 here equals to 2 here. For example, to get that point, which is point 1, first row and second column, you're taking first row from here, second column from here, and making dot product between them, which is A11 multiplied by B12 plus A12 multiplied by B22. To get this point, you need to multiply A31 by B13 plus A32 multiplied by B23. And this is the result in that row and that column in the output, which clearly will be 4 by 2. Here is another example. Let's say you want to multiply two matrices 1, 2, 3, 4, 5, 6 multiplied by 3 by 3 matrix 1, 1, 2, 0, 2, 3, 0, 1, 1. So this will be our matrix A, and this will be our matrix B. Now, first of all, we need to detect if it will work at all, if you can do multiplication. So let's check the dimensions. So this one is 2 by 3, and this one is 3 by 3. So inner dimension fits, which means you can do the multiplication. The result will be 2 by 3, so it will be 2 rows and 3 columns. So this will be the shape. Now, let's see how we do that. First of all, we're taking first row from here and making dot product with the first column like here to get that element here. So it will be 1 multiplied by 1, 2 multiplied by 0, and 3 multiplied by 0. So the result will be 1. Now, to get second element, we still need to take first row, but now we take second column and multiply dot product between the first row and second column. So here you will have 1 multiplied by 1 plus 2 multiplied by 2 plus 3 multiplied by 1. And the result will be, of course, 8. Now, if you want, for example, that element, then you need to take second row and second column. And this will be computed as 4 times 1 plus 5 times 2 plus 6 times 1, and it will be 6 plus 10, 16 plus 4, it will be 20. Similarly, you get all of the other elements, and they will be 1, 8, 11, 4, 20, and 29. To summarize, each ij element in the resultant matrix is a dot product of row I of A and column j of B. There are multiple important properties of matrices that you need to know when working with them, but the most important property is that multiplication of A by B is not always the same as multiplication of B by A. This is the most important property that you always need to remember. So it's generally not true that AB equals to BA. So let's see some simple example for that. Let's say you're multiplying matrix A, which is 1, 2, 3, 4, by another matrix B, which is 2, 2, 1, 1. So this is matrix A, this is matrix B. So when you compute it, you'll get 4, 4, 10, and 10. Why? Because this is 1 by 2 plus 2 by 1, it will give you 4. And then, for example, to get that number, you take in the last row and last column, making dot product. So it's 3 by 2 plus 4 by 1. It will give you 10. You get 4, 4, 10, and 10. Now let's reverse it. You want now B by A. You'll have matrix 2, 2, 1, 1, 1, 2, 3, 4, and the result will be 8, 12, 4, and 16. To see that this is completely different, you can check just the first one. So it's 2 multiplied by 1 plus 2 multiplied by 3. It's clearly not 4. It will be 8. So it's 6 plus 2. So this matrix is not equal to this matrix. And because of that property, it's very useful always to say if you are multiplying by matrix from left side or from right side. You always need to mention that. Otherwise, it's not clear when you multiply by some matrix. Sometimes you multiply from the left, and sometimes you multiply from the right, and the results might be completely different. So, a few more simple options, a few more simple properties of the matrices that we need to know are here listed in that long list of properties. First of all, you can change the order of addition in the matrices. So it's very simple. A plus B equals to B plus A. You have distributive law working with multiplication similarly to what you have in dot product. So sum of two matrices A and B multiplied by matrix C, if it works, if all the dimensions are fine, is the same as multiplication of AC and plus the matrix BC. Similarly, if you multiply from the left by C, you have exactly the same law. So this was from the right, and this was from the left. Now, if you multiply A by identity matrix, and identity matrix is just diagonal matrix, which has on the main diagonal ones, and everywhere else is just zeros. So zeros everywhere except that main diagonal where it's 1. So if you multiply by that matrix, it doesn't matter from which side you multiply by it. It always equals to the original matrix A. So if you multiply I by any other matrix A, it will be always A. Now, if you multiply scalar number alpha by A and making transpose, basically you can take that alpha number out of the parentheses here and make A transpose. So you basically transpose in the matrix itself without taking that parameter in consideration at all, and then multiplying by that constant. If you're doing twice transpose of the matrix, you get your matrix back. And it's simple to understand. If you're taking that kind of table of numbers and you're flipping it twice over the diagonal, you will get back the same matrix. Now, this property of transpose is much more important and more interesting. If you multiply matrix A by matrix B and then making transpose of the multiplication, then it equals to B transpose, which is the second matrix transpose, multiplied by the first matrix transpose. Pay attention to the order of the matrices, because this is very important, that you're changing the order of B and A. If you're multiplying A by B and doing transpose, then the result will be B transpose A transpose, and not A transpose B transpose. Those are completely different things. Note that this is also true only if this multiplication exists. So dimensions should match to make that multiplication true. Okay, we talked about addition of matrices, subtraction of matrices, multiplication by vectors, multiplications of matrices, and so on. So how about matrix division? I know that some inexperienced students are trying sometimes to write something like that, matrix A divided by matrix B, but technically speaking, this is nonsense. You cannot divide matrix A by matrix B. Direct division of two matrices is not defined. But what is possible to do is to multiply by inverse matrix if this inverse matrix exists. So technically, inverse matrix is defined the following way. We'll write that as B minus 1 is inverse matrix of B, and it's defined the following way. So B minus 1 multiplied by B should give you identity matrix I. Then this is inverse matrix of this given matrix. So if somebody gives you matrix B and this matrix is invertible, and invertible means that this thing exists, then this matrix, which is kind of difficult to compute, but you don't need to compute that right now because you have computational tools like MATLAB. This is how it's defined. So this is some other matrix. This is not like 1 divided by B. It's just some other matrix, which when multiplied by the given matrix B will give you the diagonal matrix. And here zeros. In that case, it also will be true that B multiplied by B in minus 1 equals to I. Now, if you want to divide one matrix by another matrix, similarly to what you did here, what you need to do, you need basically to multiply by B to the power of minus 1 from left or from right. So those will be completely different things. So this is the kind of divisions that you could expect. So this is basically A multiplied by B inverse, or B inverse multiplied by A. And those things might be completely different. So you need to be very careful with those things. So if those two are not the same, we need to be very careful when we're solving some sort of matrix equations. We need to be very consistent if we multiply by matrices from the left or from the right. Let's take a simple example. For example, we have to compute the matrix C from a given equation. So this is our example. We want to find matrix C when we have invertible matrices A and B that satisfy the following equation. The equation looks like that. Let's say AB squared plus ACB equals 0. So you want to find C out of that equation. Now pay attention that we have clearly temptation to cancel A and B with those things, but since you cannot divide by matrices, it will not make any sense. What you have to do is to multiply from left or from right by some invertible matrices to cancel some of the terms. For example, in this case, since we know that A is invertible, you can multiply from the left by A minus 1. So I will multiply both sides by A minus 1. And pay attention that this one is not number 0. This is essentially matrix all zeros. Something like that. Because all of the dimensions should match. Now, I'm multiplying by A inverse from the left side. And then this is what I will get. So it's A to the power minus 1 multiplied by A, B squared plus A minus 1. And this is because I'm using distributive law. And then A, C, B equals A to the minus 1 matrix 0. Now, this is still 0 because no matter what you multiply by matrix 0, you get still matrix 0. Those things are cancelled because this thing is I, and I multiplied by anything is that second matrix. The same thing here. This part is I. So I multiplied by b squared is b squared. So that entire thing is b squared. And that entire thing is cb. So let's rewrite it. We get b squared plus cb equals 0. Now I want to multiply by b inverse because b is invertible. And this is what I will get. It will be b squared, b to the minus 1 from the right, plus cb, b minus 1 from the right, 0 multiplied by b from the right, which is again 0. But now this will cancel with this one, and those two will cancel because it will produce I here and I here. And this is what I will get from here. So I will get here b, which is left from this one, plus c equals 0. Now I simplified it enough that I can say that c equals minus b, and this is my solution. So this is the correct way of solving equations with matrices. You cannot do just some simple calculations or simple cancellations of matrices or vectors inside of that equation. You need to go all of the way through to get to that solution. As I said before, computation of inverse matrix is kind of complicated, and there are multiple approaches exist to compute elements of the a to the minus 1 matrix. But the easiest way is, of course, to use computational tool like MATLAB. In MATLAB, you just write a to the power of minus 1, and it will give you inverse matrix. Now, for second order matrix, like matrix 2 by 2, very simple formula exists. So technically, this is 1 over, for matrix A, B, C, D, this is 1 over AD minus BC. We will see later in the future that this is basically determinant of that matrix. And here you basically switched the numbers A and D and added minus to the second diagonal numbers. So it's minus B and minus C. So it's technically easy to compute for second order. Solving system of linear equations is a very popular task in engineering in general. So general system of linear equations could be written like that, which means our variables will be x1, x2, and so on until you get to xn, and you will have n linear equations with n variables, and all of the a coefficients will be constant. So pay attention that I'm intentionally using coefficients with indices like in the matrix, because we can fit that system of linear equations in the following structure. We can write the entire system as multiplication of matrix by vector equals to vector. And then we need basically to solve that kind of equation. So pay attention why this is so. Let's take the first equation. So B1 on the right side equal, you are taking first row in the matrix and multiplying, making dot product with that thing, which will be a11 multiplied by x1 plus a12 multiplied by x2, and so on until you get to a1n multiplied by xn. But pay attention, this is exactly that equation. The same thing happens with all of the other rows of the matrix. So technically speaking, that matrix A multiplied by that vector x equals vector B. This is our equation. This is AX equals B. This is a system of linear equations in matrix form. How we solve that kind of equation? Since we know already about inverse of the matrix and we know how to solve some of the simple equations in terms of matrices, it gives us extremely simple solution. You just multiply both sides by A inverse if it exists. And this is what you will get. So this will be cancelled because this thing is identity matrix. And identity matrix multiplied by x will be the x itself. So from here, x equals A inverse multiplied by vector B. This is our solution, as simple as that. all you need to do to solve that complicated system of equations is just to find inverse matrix of A and multiply it by a vector B, which is here. This is a solution. Let's take a simple example. Let's say you have system of equations of order 2. To make it simple, 3x1 plus 4x2 equals 3. 5x1 minus 7x2 equals, say, 0. Now, in matrix form, you can write it the following way. So this is equivalent to the following matrix form. I'm just writing the coefficients in the matrix: 3, 4, 5, minus 7. Those are coefficients that I took from here. Multiplying them by x1, x2. And it equals to those coefficients, which is 3 and 0. Now, all I need to do is to find x1, x2. Those will be 3, 4, 5, minus 7, multiplied by 3, 0. And here I need inverse of that. Okay? So let's find that inverse. So let's see what it is. Just to remind you the formula for the second order, the inverse matrix of A, B, C, D, you need to make here 1 divided by determinant, which is 3, multiplied by minus 7, minus 4, multiplied by 5. And in the matrix itself, you need to make minus 4 here, minus 5 here, and to switch A and D, which will be minus 7 and 3 here, and to multiply by that vector again, 3 and 0. Okay? The result will be minus 1 over 41 multiplied by minus 21 minus 15. So the overall result will be 21 over 41 and 15 over 41. So this is our x1 and this is our x2. This is the solution of that system of equations. Done.